Disruptors and curious minds, welcome to another episode of Thinking on Paper. Today's episode is an exciting continuation of our conversation about space-based solar power. Yes, harnessing the power of the sun, beaming it to the earth, creating a sustainable, more affordable means of power. Mark, what are you psyched about to dive into in our talk today?
For this episode, I think if we put on our imaginary hats, go 100 years into the future, space-based solar power is the dominant power source. Fossil fuels are an echo from the distant past of humanity. Launch costs are negligible. Space infrastructure is self-replicating. And space is in the forefront of everyone's imagination, everyone's knowledge, because our energy is coming directly from space. But what's it going to take politically and culturally to get there? And that's why we're very happy to have Martin Soltau on the show today. He directed the UK government study into the viability of space-based solar power. He's a successful leader in the aerospace sector, a member of both the IAF and the IAA International Committees on Space Solar Power. So if anybody knows, he will know. Thank you for joining us, Martin.
Let's set the stage. I think it was Queens University Belfast. There was an experiment, something that you did that no one else had done previously. Walk us through that a little bit.
Perhaps worth saying why we needed to do this experiment. A solar power satellite, as it goes round in the orbit, to deliver baseload energy, 24/7 continuous energy, you have to continuously harvest the solar energy and you have to continuously beam it. And so somehow you either have to steer your solar panels to continually point at the sun, or you have to steer the energy beam onto the receiver. And the unique thing about our solar power satellite design, Cassiopeia, is that we can steer the energy beam through 360 degrees with no moving parts. It's a phased array, but it can steer through 360 degrees, which is very unique. It's a three-dimensional phased array. And so the experiment in Belfast with Queens University was to demonstrate this, and it was a world first. It was a small-scale model of our large solar power satellite, which is a beautiful helical array of antenna. And it was a world first to demonstrate this ability to steer the beam through 360 degrees, and we also demonstrated this ability to provide a retro-directive pilot beam from the receiving antenna to the pseudo-satellite. It was massively successful. It gave us a lot of information to allow us to validate our computer modeling, and it demonstrated this core ability. So a real milestone.
The reason why that's so special is it because if you don't beam it instantly and you don't convert it instantly, you got to store it.
It's partly that, but so we don't have storage on the satellite because storage is very heavy, and the whole design intent is to minimize the mass of what you've got to put into space. But it's mainly because reliable baseload energy, to continuous 24/7 energy, is really what's needed on Earth to provide our continuous and affordable power. By being able to make this sort of rotating joint between those two functions electronically with no moving parts, our satellite is much, much lighter and more compact than other designs. So there are designs of satellite out there that have big, heavy, mechanically driven solar panels or reflectors. Some designs don't even bother to try and have continuous power. So at 6 o'clock in the morning and 6 o'clock in the evening, the panels are edge on to the sun, so they don't provide any power at all. And that's still got utility, but not nearly as much as providing continuous power.
So walk us through the conversion process.
Cassiopeia, the design, it looks like a sort of helix in the middle. Imagine a spiral staircase twisted through 180 degrees. And that's the power core. So that has the photovoltaics integrated with power electronics, which convert the electricity into high-frequency radio waves, just Wi-Fi frequency, just like we have here on Earth, and the little antennas. So that's the power core. And top and bottom of that helix, we have these large primary reflectors that are always pointed at the sun, and they direct and concentrate solar energy onto the PV. So the chain of energy is that we could create electricity from these photovoltaics on the tops and bottom of the steps of the helix. It's converted into high-frequency radio waves, and that's done pretty efficiently. At today's components, you can get up to sort of 85% efficiency in conversion. And then the antennas form this large transmitting array aperture, which just like a phased array radar on a ship or an aircraft, it forms this coherent collimated beam at a single frequency down to the Earth-based receiver. And the reason we use, in our case, 5.8 gigahertz is that at that frequency you can transmit through the atmosphere and even heavy weather with almost no loss. So there's very minimal loss through transmitting, even over 36,000 kilometers. And then on the ground element, there's a receiver, a large receiver called a rectifying antenna or rectenna, and that comprises these little dipoles that are tuned to convert the RF back into DC electricity. Again, it does that very, very efficiently, more than 85%.
How big is that?
For our large, most economic systems, they're about 1.4 kilometers in diameter, and the receiver on Earth is between 2 and 3.5 kilometers in diameter, depending on how much energy you capture. And you can imagine the beam in cross-section is like a sort of Gaussian profile. So you've got a peak of the energy in the middle, and it tapers off a great deal towards the edges. So you build the rectenna to capture 80 to 90% of the beam. It's not worth capturing the whole lot, otherwise the rectenna would be way too big. Then you convert that DC into AC electricity just through a normal inverter. To the energy system, this rectenna looks like a gas-fired power station or a nuclear power station. It provides continuous, reliable 24/7 energy. People kind of worry about, well, how can this be efficient with all these conversions from photons to electrons to photons to electrons again? Overall, if you measure from the sun to the plug on Earth, it's about 18%, 18% efficient. If you do the same calculation for terrestrial solar, you get between 1 and 5%. Because you've got night and atmosphere and weather and seasons and so forth. So the efficiency is actually quite high and big part of the economics. I think the other part of the economics is that if you have a solar panel in space, you've got very high solar installation, to 40% more than you have at the very, very peak in the kind of midday desert on Earth. And you've got no night and things. You generate 13 times as much energy from that same solar panel than if you'd put it on Earth, at least in the northern hemisphere.
You said from sun to plug, it's 18% efficient.
That's it.
So how does that compare to like coal-fired generators?
Well, if you compare it with a gas-fired generator, which are the very efficient ones, they can be up to 60% efficient. Coal is a fair bit less, depending on the technology. You've got different metrics because you have to mine the coal or drill for the gas, and then you have to pay for the gas, whereas the sunlight is free. I think the point is, for your listeners, efficiency is quite important where the fuel source is finite and perhaps expensive. When your fuel source is free and limitless, efficiency just determines the capital cost, the capex. As long as the capex works out and you get an economic levelized cost of electricity, it doesn't really matter how efficient it is. So there's an interesting trade, because space launch is still a big part of the capex, even though the costs have come down. You want to minimize the mass, and it might be better to actually have slightly lower efficiency but lower mass.
You say that the receiver on Earth needs to be about 2 kilometers across to collect the beam. Can that shrink? Because politicians, their constituency is what really matters. People are used to having wind farms spoiling their view. They want another renewable technology is going to spoil their view. How small can it become?
Yeah, it's a really important point. These systems they're quite low impact. They're flat. They're built just off the ground, but they're like a sort of sparse mesh-like structure, potentially on poles. They're transparent, very transparent. So they let rain and sunlight through, so you can grow crops underneath them. They could even be overlaid over an existing solar farm to make best use of the grid connections. Or if you're talking to National Grid and Crown Estates about putting them offshore, and because it's involving power beaming, even though this is safe and regulated, and there's everyone has Wi-Fi routers in their house and quite happy with it. Nevertheless, acceptance of new technology is a really important thing that takes time to get the public comfortable with. And so for all those reasons, I think the early systems would be offshore, or at least well away from centers of population. But they're fundamentally sparse, low impact structures, which are nothing like big vertical wind turbines, and they won't look like sort of bleak black solar panels.
Okay, just that I'm thinking as a constituent here, if you put that system out at sea, I don't believe I'm asking this question, but I'm going to ask it, won't it cook the fish?
No, sadly, no fried chicken and no boiled bass or As much as I'd like to be a kind of Bond villain, sadly, these are not capable of doing disruptive damage like that. The peak of the RF high frequency radio waves is about 230 watts per square meter. It's less than a quarter of the peak intensity of the sun on Earth. RF is at these frequencies. It's non-ionizing, and this is why that the receivers are large, because actually the energy density is relatively low. It's 4 times the energy density of solar, so these things are much smaller than solar or wind, but it's still low compared to a nuclear power plant, for example.
Is it safe to say this same stuff, same frequency, similar frequency to what we're roaming about in large office buildings to connect our iPhones? The same thing we're literally swimming in right now.
Exactly right.
But I think it's a perception thing.
Yeah, we've done a lot of public outreach, including a big structured survey which was organised by the Royal Society, and so they got 120 members of the public from all over the UK, and actually once they understood why it was safe, they were fully supportive. The public understand the importance of reliable, affordable energy. It's fundamental to our quality of life and to our well-being, and they get very much by and large that we can't do this energy transition relying on weather-dependent wind and solar, and that we need to look at these more capable sources of clean energy. And the second point, as just saying, it is once also they realise this is not large, industrial infrastructure in their backyards, so it's safe and it's not going to affect their lives. In fact, it's going to enhance them because their energy bills are going to come right down. And the latest work we've done, the economic work, and we've just finished a technical study, is that this really can be energy at below $30 a megawatt hour. And that is broadly with today's launch costs. If launch costs come down, the cost of space-based solar power is around $10 a megawatt hour. This is insanely cheap for baseload.
Can you give us a comparison for our listeners just so they can visualize what that is compared to other energy sources?
Yeah, so things get subsidized and taxed, so they're distorting things, but broadly nuclear is well above $100 a megawatt hour. Gas in the UK is about $65 a megawatt hour. Wind is about about $82 a megawatt hour at the moment. Those are the kind of wholesale prices, and then the retail prices you pay are kind of more than that, but they're influenced by the wholesale prices. So the point is, this could be a tenth of the cost of nuclear or less.
People that are using Claude, people that are using ChatGPT, people that are creating startups using AI models don't really understand that they're connecting to these large facilities that are the size of cities. The power capacity and the redundancy systems in there are tremendous. What's your pitch to the data center providers?
The pitch to data centers is that we can provide this reliable, continuous, affordable energy. We've talked to Google and OpenAI and Amazon and co, but actually they want to just procure energy they can buy tomorrow. So whilst they're super excited by what we're doing, they want to engage with us when we're ready to promise them an energy contract rather than to support our development. There's been some incredible predictions. I think Eric Schmidt said that he can foresee that 99% of the US energy could be consumed by data centers and AI in future. That's why people are looking at data centers in space, because you've got abundant energy there, which initially seems insane, but it starts to make more sense when you look at some of the economics of this. The other challenge with data centers is getting grid connections is really, really difficult. Here in the UK, I suspect it's the same in the US and France, that you've got big lead times, like more than a decade, to get a grid connection. And space-based solar power can provide off-grid power. So you can build a rectenna over your data center or next to your data center, and you're off-grid power.
That would seem to me like a really interesting proof of concept to get going with a data center provider and just say, hey, let's power a rack. Let's power a 20 kW rack full of AI stuff with space-based solar power. But the cost of that might be pretty insane, right? At least at the moment.
The beautiful thing about space-based solar power is that it's supremely scalable. Space Solar has a roadmap where we're going to be developing and demonstrating end-to-end power from space within 5 years. So that's generating about a megawatt in space from a low Earth orbit. It's an 80 by 80-meter spacecraft. And because at that small scale, you don't get very much power on the ground, but it's a meaningful power. It's the right sort of power density, and you've got pretty much all of the technology demonstrated. A year later, we've got our minimum viable product, commercial system. But then after that, you've created all of the supply chains, the technology and things, and it's so modular that you can start to scale very rapidly. So by the mid-2030s, we'll be building these much larger economic systems and scaling them ultimately to tens of gigawatts per annum. The scale is everything, both for meeting the kind of burgeoning demand of clean energy from all nations, and particularly kind of technology like AI and robotics, in a way that it's very difficult to see nuclear being able to scale at anything like that. It takes 20 years to build two gigawatts, let alone tens of gigawatts per year, which is what we're proposing.
5 years is not a very long way. So you're talking about taking a megawatt from space and converting that through your 18% efficiency mechanic to a specific amount of power landed on the ground, applied and used. That's 5 years away.
That's right. And this is because, although there are lots of engineering development to do, we're fundamentally using today's technology in solar panels, in terrestrial robotics, in power beaming. We're not trying to invent new materials, new physics and things, which is what the fusion teams are trying to do. They're still trying to work out how to hold the sun in the palm of their hands. We've already cracked the fusion problem. We're just using the beautiful fusion from the sun.
There will have to be some new technology, some new materials, especially with self-assembly in lower Earth orbit, with maintenance of that, which will be done autonomously, I suppose, by robots.
Yeah. So what I mean by kind of no new physics, no new materials and things, is that this is about engineering the economics. So we've built very sophisticated robotic assembly machines on Earth. We think of a sort of Amazon warehouse. Now we've got to lightweight it massively. We've got to make it reliable in the space environment. Those are engineering challenges, but we know how to do that. We're good at, we can do that, and we know how to do it. Engineering the economics is really the challenge. So because it's so mass driven, because you've got to launch everything, you've got to keep the mass down. It's making these systems reliable and lightweight in the space environment. Our forecast is that with pretty much today's technology, we can get to $30 a megawatt hour. Even if we were providing it at $100 a megawatt hour, that is insanely attractive to the energy market, because you're providing not only base load, but it's dispatchable, i.e. it balances the grid, and it's exportable. So it's hugely flexible.
What space laws need to be figured out before all of this stuff can happen?
Good question. We're going to be assembling these very large systems in space, which we've only really done with the International Space Station. And this is going to be very, very different, done remotely with autonomous assembly systems. And doing that reliably, sustainably, not creating debris, I believe needs strong collaboration with regulators. Inherently, it's because the design of the solar power satellites is essentially like sort of thick paper. It's that sort of consistency. So you don't spoil off debris if you get hit by micrometeorites or something, or if you have an accident. But nevertheless, that is one area of regulation. There's establishing spectrum through the International Telecoms Union. Whilst it integrates supremely well into our energy systems, there are novel aspects to it, particularly the ability to switch the beam like an interconnector without wires, and there will be important security, cybersecurity aspects and physical security things for these systems. I think these are going to be very strategic assets in space, and with the we're seeing space increasingly being a contested kind of security and military field, and so that's an important consideration. So I think for all these reasons, there are a number of kind of stakeholders, state and regulator stakeholders. We're already engaging quite closely with them. We're engaging with Defence, with the Civil Aviation Authority, Ofcom, and the ITU here. So, and there's real willingness and excitement by the regulators. I've never seen regulators excited before like I have with space solar power.
Wow.
Bit of an oxymoron, but yeah, no, it's good.
So Mark and I recently read Machines of Love and Grace, which was written by Dario Amodei, founder of Anthropic. There's a moment referenced about Eisenhower and atoms for peace. And what happened when nuclear came up, it was like, all right, this is pretty groundbreaking, but man, how do we get our arms around it? Does space-based solar power need an Eisenhower right now to get people together? And what could that individual look like? Characteristics, abilities, capabilities, sensibilities?
That's a really great question. It does need some sort of really visionary champion who's a big leader. And must say, it'd be interesting to see who is picked for the NASA administrator, because one of the hot tips is Steve Quast, who's a really strong space-based solar power advocate, and he really gets the big picture of where space is going with the ability to assemble large infrastructure and really open up a new economic horizon and things. So you could see if somebody like him got into authority and really stirred the imaginations of another, Kennedy, saying we got to do this, as humanity has got to do this. It would change the conversations completely. I think in the UK, whilst we've got a lot of government broadly supportive, governments are naturally cautious. They're risk averse. They don't want to be kicked out by the electorate for making mistakes or taking risks or being seen to look stupid in front of the media. And so it's really tricky to get the average government to really be bold and ambitious. But ultimately it does come down to individuals who, as you say, like an Eisenhower moment, say we need to do this. We need to be bold. We need to, because the rewards are immense for the whole of humanity. Sadly, as a human race, I think we have to come close to sort of catastrophe before we realize that we need to change course. Thinking back to earlier this year, there was a huge blackout in the whole of the Iberian Peninsula over Spain and Portugal. It had almost days without any power in quite benign weather conditions. 7 people died directly as a result of the unexpected loss of power. Hundreds of thousands, probably millions, were greatly inconvenienced. People reliant on energy for their perhaps medical devices and all the rest of it. Sometimes it takes something like that to make politicians wake up and say, my God, the trajectory we're on, business as usual, is not the right course. We've got to look at these more capable systems.
Since we're on humanity, one of the things that always comes up again is, yes, but politics. And reading about space-based solar power and what you mentioned earlier about taking the energy off grid, putting nets over your data centers, this idea of like sovereign energy sources, of states now that don't have access to fossil fuels being able to have their own energy sources, big tech being able to move off the grid and have their own energy sources. It's decentralized. That's real decentralization. It sounds crazy that governments will allow that to happen. Like, you're in great contact with the UK government, I believe, the UK Space Agency. I don't know how the UK now is connected to the rest of Europe in regards to space-based solar power, to America, to China. How do we bridge the political problem of this?
Yeah, that's a great question. I think, again, another attractive things about space-based solar power is it doesn't, from an operational and energy system perspective, you don't need to have to sort of build a global grid to make the whole thing work. You could envisage one nation building its own sovereign system, demonstrating it, and then, because it fits into our existing energy networks and grids supremely well, it can grow. Whilst we strongly believe that we need international partnerships for all sorts of reasons, I also believe that this has got to be developed in a very commercial way by commercial companies rather than by big national space agencies or some horrific kind of international consortium sort of government-led thing, which would be very expensive and take many decades and probably result in just a sort of very slow research program. We've got the technology. We've done enough studies now to know that this is both economically and technically viable, and we need to get on and demonstrate small-scale systems where the international agreements are most needed is to make the common standards, make sure these things are developed responsibly, but also so that your solar power satellite can interoperate with my rectenna. And so we build this very vibrant market of competing but also collaborating designs. And so I had a wonderful meeting a couple of years ago with the Under Secretary General of the United Nations, Mamouna Sharif, and she was the director of UN Habitat, which is responsible for sustainable cities. And she was super excited by space-based solar power because she pointed out that it really democratizes energy access, because the local mayor can just build a rectenna, which is kind of the cheaper part of the system, and then receive energy from space. They don't need to own the expensive space assets. And so those standards, international standards, to make those systems interoperate, I think is going to be very important.
Let's go back on the philosophical side of this thing. When you have a resource, a resource, whether natural, whatever it is, a resource that can help people, and then you have entities that are trying to control it. An entity that controls this valuable resource has the carrot, like, hey, if you behave to our rules, we'll let you have access to this thing, and if you don't, here's the stick that follows. How do humans get out of the way?
So I think in one respect, because these are just like any other energy generation and transmission technology, to some extent it will be developed largely commercially. It'll be regulated by governments in different countries, but it'll have its own force of providing this very economic, reliable energy. And so from that perspective, it's about just making sure this new technology is regulated to be safe and secure. Getting it going from where we are today to being a thing really, powering our televisions in 10 years' time, that needs these bold leaders to say, I'm going to take a risk. The benefits are so huge here. We're going to do this, and it's no regrets, because even if for some reason we can't foresee it ends up proving too expensive or too difficult, there are so many really important disruptive technologies that we're going to be creating along the way in power beaming and the ability to build these large structures in space routinely and regularly.
Which of those adjacent technologies are you most excited about? I mean, a while ago we had on the founder of StarCloud. They're building data centers in space, and towards the end of the show he turned on his sci-fi brain and he went deep about where humanity could go with space manufacturing and space engineering. I was wondering if you could paint your sci-fi picture of that. There's not science fiction that is actually going to be reality sooner rather than later.
We know the StarCloud guys really well. I mean,
excellent.
The technology that we're excited about, the underpinning technology, I think, are these very, very light integrated large solar arrays. We're working with particularly University of Cambridge on this. They're going to be transformative, and for technologies like large scale data centers in space, being able to have these distributed computing and integrated thermal management and large scale abundant power is just transformative. I mean, abundant energy in space is not a thing yet. We're completely power constrained, and so that's restricting everything. Elon Musk has unlocked the access to space, but now it's power in space. Once you can do that, I think the next thing is getting really good at building these large structures in space. And again, SpaceX shows that, if you launch 3 times a week and not 3 times a year, you get really good. You practice, you learn, you get really good at things. And this is what's needed to get really good at rendezvous proximity operations, to do these, building these systems. We've already built a demonstrator of how we envisage building these kilometre scale structural trusses in space. There's another technology which is very precise timing across very large arrays. We've got some super cool technology that's got lots of different applications. And power beaming is a critical technology that's going to be really important for providing power on the moon, to kind of cislunar applications and asteroid mining and things. Energy and resources is absolutely critical, and power is everything. And the first thing we need to do is to be able to afford all this. And cheap energy underpins everything we can do on Earth. So there's a sort of always stepping stones to disruptive new technologies, and space-based solar power as it unlocks cheap energy on Earth. It unlocks the ability to build these large structures in space. It unlocks a huge market demand driver, because you've got to have a commercial market and not just go at the pace of government funding. It's absolutely fundamental to our next economic revolution in space.
I'm walking away from this chat very inspired. Congrats to all the stuff you've been doing, and we can't wait to see where this thing goes.
Well, thanks. It is super exciting. Timing's everything, isn't it? And everything's come together. And I just go back to your earlier point about the sort of cultural things. I mean, I do think there's a real force for good in space-based solar power, in that it provides abundance, and it doesn't provide abundance selectively to those who have already. It provides abundance to those who haven't. And that's just really, really important. You can see all the problems we've got pretty much around the world of people who haven't got enough, feeling aggrieved, and it causes massive geopolitical problems. So I'm sort of super optimistic from that point of view as well. And if we can, if we can behave more sensibly and rationally as a species through these sort of things, we can achieve massive things.
If we develop this and it's just another way to concentrate and amplify power to the things that already have it rather than distributing it, that's the key puzzle, I think, to all of this. Mark, closing thoughts? What are you thinking?
And what have we missed? What question does people not ask you whenever you go somewhere and you wish that they would?
Couple of things we haven't talked about. These are large systems, at least the RF versions, which are the ones that are going to provide the baseload, grid scale, gigawatt scale power, as opposed to laser or mirrors in space and things. But they are large, which is their one drawback. And financing the first of a kind needs many hundreds of millions. It's not billions, interestingly. And for an energy infrastructure, it's pretty small change, but in space terms, it's quite large. So getting the public and private finance together, and where typically private capital wants returns in a kind of within a 10-year time frame, and it's looking for kind of risk averse, and it's happy to funding software as a service, but not deep tech and hardware. So that's the big challenge we're fighting at the moment, and it really needs governments to pump prime and provide confidence for private capital to come in, that they're not going to be left high and dry. And the second thing, I think, probably is the international partnerships. There's some great work going on in Japan, and the kind of US military, DARPA and USA FRL and NRL, and some really interesting research in China and Japan and Korea, and of course the UK. We do need closer international collaboration. As Space Solar, we're reaching out, building those sorts of partnerships. Whoever funds this is going to have huge economic advantage for their nation. So the manufacturing of these systems alone in semiconductors and all of the components and technologies and systems is huge. It's going to create massive high value jobs and economic growth and things. For the developing nations, it's important that they have a share of that economic growth.
As you were thinking about the finance piece of this puzzle, is there anything we can learn from electrical co-ops in the way that they're organized?
Absolutely. I mean, I think there are a range of models that work already. I don't think we need to invent too much that's new in the financing. I think it just needs a little bit more risk capital. A philanthropist, a high net worth, could make this happen. I do think it needs sort of governments to come in, but there's these SMR models. Case in point, the sort of funding we're talking about is very similar to that. So, small modular reactors. There's insane amounts of funding going into fusion research, and the fusion industry. I'm a strong proponent of carrying on fusion research, but I think it's, there are billions of dollars going into that publicly and privately, and yet it's many, many decades away, with great uncertainty about whether it can ever be commercialized at a reasonable price, and certainly impossible to see how it scales. So there's lots of breakthroughs needed to make that something that would really impact our lives from clean energy. If we had 10% of what was going into fusion, space-based solar power would be a reality.
The more I hear, the more we speak to people about space-based solar power, the more sense it makes, like this decentralized, democratized access to energy. My only worry is that most of those geopolitical problems we speak of are down to A, religion, or B, energy. So I think there's a cultural stumbling block to overcome there. But otherwise, yeah, awesome. Thank you for painting us a very optimistic picture of where this can go.
Yeah, Mark, we'd love to stay in touch and do some check-ins with you as you hit different milestones in your journey. You've already hit a bunch of them. Like, with what's coming next, we'd love to track your journey and advocate for what you're doing, because I think it's phenomenal.
Oh, I'd love to stay in touch. I mean, we're just one part of a chain that goes right back to Peter Glaser in the cities. These sort of big visionaries. John Mankins done a great deal, and these are the people who've kind of saw what the vision was way before reusable launch was a thing, and we're just picking up the candle and keeping it going.
Mark, do you want to end with a closing question? Do we want to do the Kevin Kelly question?
Kevin Kelly was on Thinking on Paper. I don't know if we mentioned that, listeners, but yeah, he was on here, and he left a question for our guests. What should humans be, and how does technology help us get there?
Humans should be kind and look out for each other and be ambitious and have creative curiosity and imagination. And how does technology get us there? Technology is so important to solve problems that perhaps non-technical people can't see a way through, and politicians can't see a way through. Very often there are really capable technology solutions, and so having lay people have greater understanding of science and maths, I think, is a really important thing. And I think free speech as well is just so important, because you have the freedom to ask and challenge and question, and because we need to think differently very often to come up with solutions that ultimately are going to make us all prosper.
It's very interesting that a lot of folks like you that we talk to, there's a very interesting thread of this kindness, empathy, curiosity, open-mindedness that is wonderful, and you hit on that very well. Appreciate you entertaining that question. Well, there you have it. Space-Based Solar Power, episode 2 of many. We're going to track this technology as it grows, and as folks like Martin are doing their thing to make this thing a reality. Thinkingonpaper.xyz is where you can find all of these episodes. Mark, closing thoughts?
Be curious, stay disruptive.
Keep thinking on paper.